All right, welcome to the Explainer. We love to break down those big ideas, and today we're diving into a principle of physics that I'm betting you've heard of, but maybe don't know as well as you think you do. We're talking about Bernoulli's principle, and trust me, it's the secret sauce behind some of the most incredible technologies we use every single day.
Okay, let's kick things off with something that honestly is just mind-blowing. Modern flight. You look out the window of a plane and you see this. A huge, perfectly shaped wing just slicing through the air. It looks so effortless, right? But it almost feels like it shouldn't be possible. And that makes you wonder, seriously, how can tons and tons of metal actually get off the ground and just fly? Well, the answer most of us got back in school, it was this really simple, kind of neat theory all about the shape of the wing. I'm sure you've seen a diagram exactly like this before. They call it the longer path theory, or sometimes the equal transit time theory. The whole idea is, right, the air splits at the front of the wing. The air that goes over the curved top has a longer journey, so it has to speed up to meet its buddy from the bottom at the exact same time. And this faster air, so the theory goes, creates lower pressure. Lower pressure on top, higher pressure on the bottom, that means lift. It sounds so perfect, right? So simple and intuitive. Well, about that beautiful, elegant explanation, it's totally, completely wrong. It's actually one of the most stubborn myths in all of physics. And you know what? Taking this myth apart is the key to understanding how lift really works.
So here's the deal. There is just no physical law, none, that says those two streams of air have to link back up at the same time. In fact, when we actually tested in wind tunnels, the air going over the top moves way faster than the theory would predict. It gets to the back of the wing way, way before the air that went underneath. That whole equal time thing, it's just made up.
So if that's not what's going on, what is? Well, to get to the bottom of lift, and a whole lot more, we need to travel back in time, all the way back to the 18th century to a brilliant Swiss mathematician named Daniel Bernoulli. He's the one who figured out this fundamental secret about how fluids, liquids and gases, behave.
And this is it. This is the core idea. I want you to just forget everything about longer paths and equal times. Bernoulli's principle is all about a direct inverse relationship inside a fluid. Just think of it like this. It's the great pressure-speed swap. It's a fundamental rule. When a fluid's speed increases, its internal pressure has to decrease. Simple as that.
Okay, so how can we actually see this in action? This thing right here, it's called a Venturi meter, and it is the perfect way to show what's happening. It's basically just a pipe that gets skinny in the middle. Now, just imagine some fluid, could be air, could be water, flowing through it. What do you think is going to happen when it hits that narrow part? Okay, so in the wide section, the fluid is just kind of cruising along, moving pretty slowly. But to squeeze the same amount of fluid through that narrow section in the same amount of time, it has no choice. It has to speed up. It has to accelerate. And what does Bernoulli's principle tell us? When speed goes up, that internal pressure has to go down.
And hey, you can prove this with a really simple experiment. See that U-shaped tube? That's a pressure gauge. It's called a manometer. And look, you can actually see how the higher pressure in the wide, slow part is pushing the liquid down. But then, in that skinny, fast-moving section, the lower pressure literally pulls the liquid up. The pressure difference is undeniable. It's right there for you to see.
But why? Why does this happen? Is it just some weird quirk of nature? Nope, it's actually rooted in one of the most fundamental laws in all of physics, the conservation of energy. You see, a fluid that's moving has energy, and that energy can show up in a couple of different ways.
I want you to think of a fluid's total energy like a budget. It's got a fixed amount of energy, and it can spend it in two ways. First up, you've got static pressure. That's the energy that's just pushing outwards in all directions, kind of like the air pressure inside a tire. Then you've got dynamic pressure. And that's the energy of its motion, the energy it has simply because it's flowing somewhere.
So, in a perfect world, a steady, frictionless flow, the total pressure, which is just the static plus the dynamic, has to stay constant. It's a closed system. So what happens if the fluid speeds up? Well, its dynamic pressure goes up. And to keep that total constant, something has to give. The static pressure must go down. It's a perfect trade-off, a balancing act.
Okay, so now we get this fundamental principle. Let's see how this one idea leads to some absolutely incredible real-world stuff, and we'll start right back where we began.
So, back to the airplane wing. It has nothing to do with the longer path. It's all about the curve. That curved top surface forces the air flowing over it to speed up, to accelerate. And what did we just learn?
faster moving air has lower static pressure. Meanwhile, the air under the wing is moving slower, so it has higher static pressure. And that difference, high pressure below, low pressure above, creates a net force pushing upwards. And that, my friends, is lift.
And once you see it, you start seeing this principle everywhere. I mean, everywhere. In an old car engine, the carburetor, it's just a venturi tube that speeds up air to create low pressure, which then sucks fuel into the engine. Those little tubes on the outside of a plane? Pitot tubes. They use this exact principle to figure out the plane's airspeed. Even rocket engines use specially shaped nozzles to turn the insane pressure from combustion into pure raw velocity.
It's even getting into high-tech robotics. These things are called Bernoulli grips. What they do is shoot out jets of fast-moving air to create this little pocket of low pressure. And that pocket is strong enough to lift really delicate things, like a piece of fabric or a super fragile silicone wafer, without ever actually touching them. How cool is that?
But, like pretty much any law in physics, this principle has its limits. And because the idea is so neat and tidy, it gets used to explain all sorts of things that, well, it really has nothing to do with.
Look, in a perfect physics textbook world, Bernoulli's principle is super clean. We have to assume the flow is nice and smooth, not turbulent. We assume the density of the fluid stays the same and that there's no friction. Of course, the real world is a lot messier, right? Air gets turbulent, there's always friction. But even with all those messy complications, the basic principle is still what's making things happen.
So what about that classic classroom demo? I bet you've seen this, maybe you've even done it yourself. You take a little strip of paper, hold it just under your lip, and blow over the top of it. And what happens? The paper lifts up. And the explanation you always hear is, aha, faster moving air has lower pressure.
And this is where so many people get it backward. The common little saying is, fast air causes low pressure, but that's not quite right. The real reason the paper lifts is because of the curve. Your breath is forcing the air to follow that curved path. And there's a fundamental rule in fluid dynamics that says, for a fluid to make a turn, there has to be lower pressure on the inside of that curve. The speed is actually a result of the low pressure, not the other way around.
But honestly, here's the biggest mistake people make. Bernoulli's principle is all about comparing the energy within one single continuous flow of fluid. The stream of air coming out of your mouth and the still air just sitting in the room under the paper, those are two completely separate systems. They have totally different energy levels. Using Bernoulli's principle to compare them is like, trying to compare the bank accounts of two total strangers. It just doesn't work.
So, let's just nail this down once and for all. What Bernoulli's principle actually says is that within a single flow of constant energy, when that fluid flows through a region of lower pressure, it speeds up, and vice versa. It's not this blanket rule that fast air means low pressure. It's really the other way around. A region of low pressure is what makes the fluid accelerate into it. The pressure drop is the cause. The speed is the effect.
So there you have it. Bernoulli's principle isn't some cute little story about equal travel times. It's a really profound idea about the conservation of energy, this constant, beautiful trade-off happening between pressure and speed. So now, the next time you see a pitcher throw a wicked curveball, or see a race car that looks like it's glued to the track, or even when you just spray a perfume bottle, you'll know what's going on. You'll know the secret of the pressure-speed swap. So my question to you is, where are you going to see it next?